In this example, we are going over exercise 355, which is a problem that says if the tension developed in each of the cables cannot exceed 300 pounds, determine the largest weight of the crate that can be supported. Also, what is the force developed along the strut AD? Now, the first thing I'm going to do is, I know the points A, B, C, and D are going to come really important here. So I'm just going to figure out what their positions are, their position vectors. I'll write them down as points in space. So you can see, for instance, that point A is 0 in the X, 6 in the Y, 2.5 in the Z, and so on. So I'm just going to quickly write these down. Hopefully you can see from the diagram how I'm getting these. Now I'm also going to do a free body diagram. And just for ease, I'm going to do it on this diagram that we're given. So we have the weight of the crate, which I'm going to call W. That's what we're going to end up finding. I'm also going to put in FAB, which is a tension force because it's a wire. It's also going to be FAC, which is along that wire, which is also a tension. Now, the hard part here is the strut. So the strut A to D, although I'm going to call it D to A, and I'm going to call it D to A because when you look at that strut, it is actually pushing outward on the rope. And so that force is actually going to go along the direction of D to A because the strut is pushing out on it. It's not a tension force, it's an actual pushing force on it. So there's my free body diagram. So I'd like to find these force vectors and write them in terms of IJK. So I'm going to start by looking at FAB here. So I'm going to use the position vector of A to B to set my direction and find a unit vector for A to B. So my position vector is going to be RB minus RA, and that's going to give me this. And my overall magnitude for RAB, when you do the calculation, it's going to give you 6.5 feet. With this information, I can now write FAB in terms of an overall magnitude, which is unknown at this point, FAB, and then the unit vector, which is RAB divided by its magnitude. So I'm going to get negative 2 over 6.5 I hat minus 6 over 6.5 j hat plus 1.5 over 6.5 k hat. And that's what I'm going to use for my force vector AB. All right, I'm going to repeat this process for FAC. So that's going to find me doing the unit vector for A to C by finding the position vector from A to C, its overall magnitude. And that'll allow me to write FAC in terms of its unknown magnitude times the unit vector in the direction from A to C. In the interest of time, I'm going to do FD to A pretty quickly here and just give you the result. Please note that the force points from D to A, so in this case I have to use A minus D. But when it's all said and done, we follow the exact same technique we did before, and you will see what the final answer is. So it's probably worth checking it out on your own and seeing if you can replicate it. And of course, the last force is the weight. And I can just write that by 0I plus 0 j hat minus W k hat. I'm using W for weight, and it's in the negative Z direction. Just to make things clear, I'm going to rewrite the forces right by each other here. We'll see why when I'm going to add them together. So this is just rewriting what I already found above, but just putting it in a neater format so you can see it all together. Now, once I have all these forces, we know the object's in static equilibrium. So all the forces of these have to add up to 0. So each component, the x, y, and z, is going to sum up to 0. This is going to allow us to write a couple of equations to solve. We can start with the x components. So I'm just going to add up everything in the I hat column and set it equal to 0. This is going to give me one equation I can use. And I'm going to get negative 4 over 13th FAB. Please notice, because the overall magnitude was 6.5 feet, I just decided to convert this into an integer denominator. So instead of 2 over 6.5, I've got 4 over 13 in that first term for FAB. So that's what I'm just doing there, is just putting it into integer form. And so I get negative 4 over 13th FAB plus 2 over 7th FAC equal to 0. I'll call this equation 1, but let's take a look at what equation 1 actually shows us. when I actually sort of move everything to their separate sides, I can find a relationship here where FAC is equal to 14 over 13 FAB. Now notice 14 over 13 is greater than 1. So this tells me that FAB has to be smaller than FAC, because if you're taking the value of FAB, multiplying it by a number greater than 1, then FAC is going to be the larger number. So FAC is going to be the bigger tension of the two ropes. I'm just going to write that down here, what we just said, to show you that FAC's got to be greater than FAB. So that's the one we're going to set to 300 pounds. Because the minute AC gets to 300 pounds, that's when the system's going to fail. And at that point, when FAC is right at that 300 pound mark, we can now figure out what FAB is using equation 1. And so we'll have our values that we can use in our other equations. You can see here FAB is just going to be 278.57 pounds. We're not going to round off yet because we need to use these numbers. At this point, it's mostly just an algebraic exercise to sub in the values and to calculate the rest of them. So I'm going to sort of zoom through this pretty quickly. You can slow it down and pause it and take a look as you go through. But it's basically taking these numbers and then subbing them into the equation for Fy equals 0 and then also Fz equals 0. And as a result, you'll see coming up that we get our values for FAD, and then we actually get the value for the weight. And so we end up with the weight being 407 pounds. All our values came out positive in this question, so that means that all my directions that were up on the free body diagram are correct as well. Of course, you want to round that off to 407 pounds for 3 sig figs, and you also want to round FDA off to 557 pounds. Well, that's the problem. Thanks for watching. Have a great day.